In game theory, the Shapley value, named in honor of Lloyd Shapley, who introduced it in 1953, is a solution concept in cooperative game theory. To each cooperative game it assigns a unique distribution of a total surplus generated by the coalition of all players. The Shapley value is characterized by a collection of desirable properties. Hart provides a survey of the subject. The setup is as follows. A coalition of players cooperates, and obtains a certain overall gain from that cooperation. Since some players may contribute more to the coalition than others or may possess different bargaining power, what final distribution of generated surplus among the players should arise in any particular game? Or phrased differently, how important is each player to the overall cooperation, and what payoff can he or she reasonably expect? The Shapley value provides one possible answer to this question. Formal definition. Formally, a coalitional game is defined as there is a set n and a function that maps subsets of players to the real numbers, with where denotes the empty set. The function is called a characteristic function. The function has the following meaning. If S is a coalition of players, then, called the worth of coalition S, describes the total expected sum of payoffs the members of can obtain by cooperation. The Shapley value is one way to distribute the total gains to the players, assuming that they all collaborate. It is a fair distribution in the sense that it is the only distribution with certain desirable properties listed below. According to the Shapley value, the amount that player I gets given in a coalitional game is where n is the total number of players and the sum extends over all subsets S of n not containing player I. The formula can be interpreted as follows. Imagine the coalition being formed one actor at a time, with each actor demanding their contribution V minus V as a fair compensation, and then for each actor take the average of this contribution over the possible different permutations in which the coalition can be formed. An alternative equivalent formula for the Shapley value is where the sum ranges over all orders of the players and is the set of players in which proceed in the order. Example. Consider a simplified description of a business. An owner, O, provides crucial capital in the sense that without him no gains can be obtained. There are K workers W1, WIC, each of whom contributes an amount P to the total profit. So N equals O, W1, WIC, and V equals 0 if O is not a member of S, and V equals MP if S contains the owner and N workers. Computing the Shapley value for this coalition game leads to a value of KP, 2 for the owner and P2 for each worker. Glove game. The glove game is a coalitional game where the players have left and right hand gloves and the goal is to form pairs. Where players 1 and 2 have right-hand gloves and player 3 has a left-hand glove. The value function for this coalitional game is where the formula for calculating the Shapley value is. Where is an ordering of the players and is the set of players in which proceed in the order. The following table displays the marginal contributions. If player 1 by a symmetry argument, it can be shown that due to the efficiency axiom the sum of all the Shapley values is equal to 1, which means that properties. The Shapley value has the following desirable properties. 1. Efficiency. The total gain is distributed. 2. Symmetry. If I and J are two actors who are equivalent in the sense that for every subset S of n which contains neither I nor J, then phi I equals phi J. 3. Linearity. If two coalition games described by gain functions V and W are combined, then the distributor gains should correspond to the gains derived from V and the gains derived from W, for every I in n. Also, for any real number E, for every I in n. 4. Zero player. The Shapley value of a null player I in a game V is 0. A player is null in if for all coalitions. In fact, given the player set n, the Shapley value is the only map from the set of all games to payoff vectors that satisfies all four properties 1, 2, 3, and 4 from above. Addendum definitions. 1. Anonymous. If I and j are two actors, and w is the gain function that acts just like v except that the roles of I and j have been exchanged, then phi I equals phi j. In essence, this means that the labeling of the actors doesn't play a role in the assignment of their gains. Such a function is said to be anonymous. 2. Marginalism. The Shapley value can be defined as a function which uses only the marginal contributions of player I as the arguments. Aumann's Shapley value. In their 1974 book, Lloyd Shapley and Robert Aumann extended the concept of the Shapley value to infinite games, creating the diagonal formula. This was later extended by Jean-François Mertens and Abraham Neyman. As seen above, the value of an n-person game associates to each player the expectation of his contribution to the worth or the coalition or players before him in a random ordering of all the players. When there are many players and each individual plays only a minor role, the set of all players preceding a given one is heuristically thought as a good sample of the players, so that the value of a given infinitesimal player around as his contribution to the worth of a perfect sample of the population of all players. Symbolically, if is the coalitional worth function associating to each coalition measured subset of a measurable set that can be thought as without lossive generality, where denotes the Shapley value of the infinitesimal player in the game, is a perfect sample of the all-player set containing a proportion of all the players, and is the coalition obtained after joins. This is the heuristic form of the diagonal formula. Assuming some regularity of the worth function, for example assuming can be represented as differentiable function of a non-atomic measure on, with density function, with, under such conditions, as can be shown by approximating the density by a step function and keeping the proportion for each level of the density function. And the diagonal formula has then the form developed by Aumann and Shapley above can be vector valued. In the argument above, if the measure contains atoms is no longer true. This is why the diagonal formula mostly applies to non-atomic games. Two approaches were deployed to extend this diagonal formula when the function is no longer differentiable. Mertens goes back to the original formula and takes the derivative after the integral, thereby benefiting from the smoothing effect. Neyman took a different approach, going back to an elementary application of Mertens's approach from Mertens. This works, for example, for majority games, while the original diagonal formula cannot be used directly. How Mertens further extends this by identifying symmetries that the Shapley value should be invariant upon, and averaging over such symmetries to create further smoothing effect, commuting averages with the derivative operation as above.